other measures of uh, other other ways to construct confidence interval or interval estimation using for mean variance, sorry, mean and proportion. Okay, Jap, let me just open up my my apa nama dia? Jom, presenting. Okay, can you see the whiteboard? Which one? Oh, can you see this one? Okay, so tell me whether you can see my writing. Okay, so in the last class we looked at confidence interval. Okay, four parameters mean. Can you see my writing? Yes. Okay. So betul ke? Okay. Okay, try again because I've closed one window. See whether you can see my writing. So confidence interval for the mean mu1 minus mu2. Oh boy. Jap. Aduh, nak masuk lagi. Okay. So we also looked at proportion, single proportion, pi1 minus pi2. I hope you can see I'm writing pi1 minus pi2 now. Okay. So we've got these two. No, okay, that means you're looking at the wrong. Okay, that means I'm doing on the wrong screen now. Yeah, let me just close this off then. Yep. New window, whiteboard. Try again. Okay, I'm writing now. Nampak? Okay, great. Okay, I'm writing CI. All right, great. So here you've got so we have looked at conflict interval for single mean, for difference between two means. Okay, we've got what else? What other parameters did we looked at besides mean? Response, please. Proportion, good. Single proportion and difference between two proportion. Okay. So note that for all these confidence interval, we always assume that our, let's say I have my proportion, my population here, and this is my sample. This is my population. In order for me to use all these formulas, I'm always assuming that my population is normal. My population has a normal distribution. That means all my observations here has a normal distribution. Okay. But in order for me to construct the confidence interval, I will need to use a marginal error, which requires me to look to requires me to use a certain distribution. Okay, like for example, if I want to construct mean and difference between two means, what are the distribution associated to these intervals? Response: what is the distribution that I use to construct this interval? Response, please. What is the distribution that I use to construct the confidence interval? I need normal. What kind of normal, Antonius? It's a certain kind of normal. What kind of normal? Uh-huh. Normal are the two kinds. One is the normal. The other one is standard normal. Standard normal, yeah, standard normal, which is a vec normal distribution. Okay, what else? Is it just vec? Is there any other choices if I want to construct a confidence interval? What are the distribution that I use? T, that's right. So I use vec or T distribution. Okay, so when do I use vec or T? It depends on whether I know my population variance or not. So here for vec, to decide whether I use vec or T, I would check whether um, I do I if it's unknown, if it so I will check whether yeah, so I will check whether my variance is known or not. Okay. If it's unknown, then I will need to check out my sample size. So if it's large, I use a vec. Okay, if it's large. If it's less than 30, less than 30, I will use a T distribution. Okay, so that's how I use my vec or T. Okay, but note that when you have the difference of two proportion, I would need to use an additional condition, which I need to check whether it's the same or not the same. Okay, so that is for uh, confidence interval for the mean. Okay, okay, ingat eh? Now, what about um, what about for proportion? What is the distribution that I use to construct my confidence interval? Listen, dia punya soalan is, what is the distribution that I use to construct the confidence interval for proportion? This is what we learned last week. Response, please. What is the distribution that I use to construct the confidence interval? Response. Also normal. What kind of normal? Amma? What kind of normal distribution? Vec normal distribution. Or, so, so basically, X can be a normal distribution, but it's not a standard normal because you know standard normal has a mean of 0. So if you look at these two distribution, the characteristics of Z and T, Z ni semua, all this has a normal distribution. Let me tukar color. So all this has got, so Z or T, okay? The characteristics of the distribution is always no apa tu symmetric with um 0 as the mean. 0 as the mean for Z, and it has a middle value of 0 for the T distribution. Okay, so it's symmetric. So that's why when you construct this interval, you always use, for example, here you use X bar for mu. Mu, you've got X bar plus minus some error. Okay, so this one also X bar 1 minus X bar 2 plus minus some error. Okay, and for here you use, for example, here you've got, sorry, P plus minus some error. Yeah? This one is P1 minus P2 plus minus some error. Okay, so you've got this you have got this plus minus sign here because the distribution that you use is symmetric. Okay, so your interval that you have here is always like this. Is 1 minus alpha here. So this is the confidence interval that apa tu? Yeah, if I shade this area here, so this area is 1 minus alpha, which is your confidence interval. So you always check. So for confidence interval, it's always 1 minus alpha to the percentage. So it is your belief. So 99% or 100%. So this is your confidence interval. That's why you can do a plus minus sign here because of the symmetry of the distribution that you use to construct. Okay? Am I clear? Okay. Right. So now, today, we're going to look at another parameter, which is what? What are the parameters that we haven't looked at? Which is the variance. Okay. So we're going to look at these two measurements, single variance and also ratio between two variance. Now the ratio actually reflects the difference. Okay. Ratio would reflect the difference, but because you know the variance cannot take in negative values. So there's no point looking at the difference, but rather on the ratio between the variances. Okay, so let's look at that. So in order to construct this interval, it's slightly different. Why? Because we're no longer going to look at a distribution which is symmetric. So we're not going to use a Z or a T. Okay, Z or T is easy because it's just a plus minus. You take a sample statistics and you plus minus some error, and you will get your interval. Now for this distribution, we're not going to look at Z or T, but another distribution with another characteristic which is not going to be symmetric. Okay. Okay, let's go back to our, let me save this as image first. Okay, going back here. Hmm, nak upload lah, boleh upload attachment, kita apa. Anyway, okay, I'm going to go back to our slide. So, can you, can, can you see, yeah, not yet. Can you see the slides now? Okay, great. Now, today we're going to do the last part of parameter estimation, trying to estimate, knowing the value of the estimate for a variance using confidence interval. So just to know, you've got point estimation, how to estimate, and then you've got an interval estimation. So we're still using this parameter estimation to estimate. Okay. Now, let's look at how to construct the confidence interval for a population variance. So for a population variance, if you take a random sample of size n from a normal population with variance sigma squared, and you can compute its sample variance, then the best point estimate for the population variance is S squared. This you already know from the first part of parameter estimation. Now the statistics for for S squared is actually chi squared. Okay, so the sample statistics for S squared is actually chi squared. So chi squared can be defined as n minus 1 S squared, which is the sample variance, divided by the population variance. This you've already seen chi squared at the end of chapter 2. Okay, remember we did it before MCO. So we look at chi squared distribution. Now chi squared distribution has an n minus 1 degrees of freedom. So in the last class, at the end of chapter 2, we looked at how to read the table. It's only how to read. Now we're going to see how we apply this chi-square distribution. And if you recall, a chi-square distribution has this shape. What does this shape? What's the name of, how do you describe this shape, class? Is it symmetric? It's not symmetric. Okay, it's positively skewed. Yes, Antonius yeah, Jason is positively skewed, in which it starts with 0. So that it doesn't have any negative values, and it's skewed, so it's not symmetric. So you know in advance that when you want to estimate the parameter, it's not going to be a sample statistics plus minus. We're still going to use the sample statistics, but in a different way. Okay, right. Let's open up my animation. Alamak, animation tak. Sekejap, eh. Right. So look at here. So based on what you have learned so far, when you want to find the confidence interval for a parameter, in this case sigma squared, our aim is to find the probability of the parameter lying between these two limits, okay? Some lower limit and upper limit. And the probability of this to happen is 1 minus alpha. Okay, so the aim to find of the confidence interval is to find these limits which satisfy this probability. Okay, so if I were to draw this chi-square distribution, okay, now one minus alpha is going to be in the middle, just like we saw for Z distribution. It's going to be in the middle value. Okay, confidence interval. Now, if this is 1 minus alpha, that means the area, so 1 minus alpha is the area under the graph. Remember, probability is always the area under the graph, 1 minus alpha. So your upper tail area is alpha over 2, and your lower tail area is going to be alpha over 2. Now, if this area is alpha over 2, and if this is a chi-square distribution, alamak, ibu nampak ke? Sekejap eh. Okay, tak nampak saya tunjuk-tunjuk ni kot. Sekejap eh. Okay, show it from here, so it's going to be easier for you. Let me just buang benda ni. Sekejap eh. View. Cuba tutup ya. Sekejap eh. Bukan slide show. Tak boleh. Sekejap eh. Tarik ni. Okay, okay. Right. Now, tadi I said that the probability is, this is our confidence interval. So 1 minus alpha is the area under the graph. Okay. So if this is 1 minus alpha, therefore my upper tail area is alpha over 2, and my lower tail area is alpha over 2. And if this is since this is a chi-square distribution, therefore the point here, at this point here, is corresponds to chi-squared alpha over 2 n minus 1. Okay, and the point here is going to be chi-squared 1 minus alpha over 2 n minus 1. This is not going to be minus chi-squared alpha over 2. I mean, well, strictly speaking, yeah, I mean, in theory it is minus, but since we don't have a minus value, so we have, this is 1 minus alpha over 2, this point here, okay, n minus 1. Now, since we want to formulate this formula to get its confidence interval, so what I need to do, I mean, making use of top right arrow to close the tab. Top right arrow to close the tab. Apa benda top right arrow to close the tab? Top right arrow. Tap right arrow to close the tab. Tab apa eh? Sorry Ali Imran tak faham. Okay, and tapi can you see my slides? Boleh kan? So now chi-squared, this is the definition of chi-squared. This is the okay. This is the definition of chi-squared. Chi-squared is n minus 1 s squared over sigma squared. So this probability here is equals to this, right? The probability of chi-squared this point to that point of chi-squared is 1 minus alpha. So I will aim to have this sigma squared here. So what I do is I just replace this chi-squared. So chi-squared is n minus 1 s squared over sigma squared. I manipulate this value so that my sigma squared will be it as my numerator. So in the end, I will have this formula here. Okay, so this formula is essentially my confidence interval. Okay, right. You don't have to, it will help if you understand how this come about. Okay, notice that, you note that formula will not be given to you, but the input for the confidence interval will be given to you based on your statistics table that you have on page 2 and 3. Is n minus 1 s squared. So note that for the two limits, you got n minus 1 s squared over chi squared. So n minus 1 s squared over some chi squared. But which chi squared do you need to use? Now there's two chi squared values here. Okay, 1 minus alpha over 2 n minus 1 and alpha over 2 n minus 1. So one of each of these will be put under the confidence in for the limits. Now since your chi squared is going to be in your denominator, therefore the bigger value for your lower limit and the smaller value will be in your upper limit. Okay? Nah ke? Tu je lah. That's it for confidence intervals. Class, do you have any question? Assume no. So I'm going to move on to an example. The following are the weights in decograms of 10 random packages of grass seed. Yes, Antonius? Okay, I'll get back to you on that. Okay, the following are the weights in decograms of 10 random packages of grass seed distributed by a company A. So these are the observations. Okay, so these observations are samples or observations from samples or observations us. These comes from these are observations from the sample or from a population, from a sample or from a population. Class. These tu je kat naik ke atas weh. Nama Nampak tak? No, alamak kenapa tak nama pula? Kenapa dia ni? So, are you saying that you cannot see my slides? Sekejap. Apa hal lah? Sekejap. I'm going. Can you see my slides? Were you able to see this slide just now when I was explaining the confidence interval? Boleh? Okay, tak apalah. Okay. Sekarang boleh. Okay. Okay, let's look at an example. So that just now we looked at, so this would be your confidence interval for your population variance. Basically, the elements consist of the definition of your chi-squared distribution, where you rearrange that to be n minus 1 s squared over chi-squared. So this is the definition of the chi-squared. So you rearrange sigma squared. This is to simplify the limits. You just rearrange the sigma squared. So you've got n minus 1 s squared over chi-squared. So this one would be your limits. Okay. And then in order to know what is the value of the chi-squared they're going to use, you're going to draw this graph, and the points associated to the lower tail and the upper tail will be your denominator. So to answer Antonio's question just now, apa tadi Antonio tanya tadi? Mana? Alamak, tak nampak pula kat atas. I cannot see atas ni. So Antonius you were asking, does it matter apa tadi Antonius? I can't go up to the message yang atas. Antonius, you were asking left to right or the other way around. Okay, so this one is so your confidence interval, the left hand side here would be your lower limit. This is going to be your upper limit. Okay, now lower limit is always smaller than the upper limit. So chi-squared alpha over 2 is the bigger value. So it makes, if a bigger value for your denominator will give you a smaller value as your limits. Okay, and this one would be 1 minus alpha. So your upper limit would have a bigger value. Okay, lower limit, upper limit. Okay, right. Okay, so look at the example here. So following are the weights in diagram of 10 random packages. Nampak Okay, so these are observations from your sample because it says 10 random packages of grass seed distributed by company A. So obviously company A has lots of grass seed. Okay, this is just 10 of them. Okay, find a 95% confidence interval for the variance of all such packages of grass seed distributed by the company assuming a normal population. Okay? Assuming normal population doesn't mean that you construct it using a normal distribution. Assuming normal distribution means that these observations comes from a normal distribution. Okay? Alamak, kenapa dia jadi macam ni? Image currently be displayed. Aduh. You guys tak nampak kan equation yang ini kan? Oh boy. Cuk, cuk. Ayah. Kenapa dia punya equation tak keluar? Yeah, wait. I'm going to stop for a while and then I'm going to open up again. Open my file again. Passport. Teaching. Just slides. Okay, bear with me. Okay, dia keluar. Sekejap So now, window. Can you see my slides? Okay. So, right. So here you have, this would be your, bukan ni, alamak, mana tadi? Example 1. Here. So this is your population. So observations from a population come from a normal this population, from a normal, it has a normal distribution. Okay. So in your apa benda, from the sample, so n is 10. So if you calculate this, you have a sample variance of 0.286. Okay. So if you want to find the confidence for sigma squared, here you want confidence interval for the variance, so it's sigma squared. So this is the formula. Okay, always to write the formula beforehand. You might get marks here. N minus 1 s squared over chi squared. So which chi squared to use? So this is for, if this is 0.95, therefore this point here is going to be 0.025. Therefore the point at this probability, area probability is chi squared 0.0259 and this is 0.9759. Okay, so just plug in the values. You plug in the values. Alamak, betul lah. You plug in the values and then you calculate. Just plug in the values and you get your limits. Okay, so I haven't calculated here, but you can calculate yourself. So what is the limit? So this would be the limits for confidence interval for sigma squared. Okay, so it's fairly direct. Okay, so that's one example. Second example, suppose the refractive indices of 20 random pieces of glass when reflected from a large optical shipment have a variance of 1.2. So this variance, is it sigma squared or s squared? Variance 1.2, is it sigma squared or s squared? S squared. Okay, it's not s, it's s squared. Okay, because it's variance of the 20 pieces. So construct a 95% confidence interval for the standard deviation, assuming a normal population. So here you want to construct confidence interval for standard deviation, not variance. In example 1, it wants the variance. Now it wants the standard deviation. Okay. So here, what you do is from this, you've got s squared 1.2, again 0.95, but this time is 20. So therefore, your degrees of freedom is 19 and minus 1. Now, the confidence interval formula that you have just now is for the variance. Okay. So if you want a standard deviation, you need to square root at each value of the limits. Okay. But I would suggest when you want to change that to a sigma, do it of the um, at the end of your solution. So here, this is the formula for 95% confidence interval for sigma squared. So you do all the calculation as you did in the previous example, and you get this value. Therefore, 95% confidence interval for sigma is just the square root of each of the limits. Okay, are we clear? Class, are we clear? Okay, good. Okay, that's done for confidence interval for a single population variance. Okay, so the challenge there is just to remember your limits. That's it. Okay, and then if you have sigma, then you just have to square root the value of your limits for your population variance. Because sometimes students think that okay, because why I wouldn't sure kan apa, I wouldn't suggest that you do it from the front, because sometimes you forget, do I do a square root for the whole of this interval or what? That's why you need to understand that these are your limit. Just these confidence interval are limits. Okay. Well, confidence interval is essentially a range of values from this point to this point. But when you calculate the confidence interval, you are getting the limits. So when you want to find the limits, your interval, you need to know what the limits are. So this is essentially is a value. This is a value. But the confidence interval is the whole range of values from, for example, 0.0069 up to 0.0256. Okay, now, right. So let's look at ratio of variances. So when you do ratio of variances, that means you're dealing with two different population. Okay, and you want to check the ratio between the population variance for these two populations. Now, similar to what we have in the previous example, in the previous confidence interval for population variance, you basically have two population. Each population, you're taking a sample size, and from that sample size, you take observation, and you can calculate its uh, sample variance for each of the population. Okay. So therefore, the best estimate for the ratio of population variances, sigma 1 squared over sigma 2 squared, is S1 squared over S2 squared. Okay. Right. Okay. But the statistics for the ratio of variances is given by, let me check the book and see whether, okay, I'm going to use F1 squared over 2 squared. Sure. Okay. Okay. This is 1. Okay. In general, in general, the estimate, if the best point estimate for the ratio of population variances is this, so it's S1 over S2 squared. Now the statistics that you use, the statistics for S1 squared over S2 squared is an F distribution. So this F distribution, oh lama, sorry, saya minta maaf Tadi betul lah tadi. I can't, alamak, silap. Oh shit, kejap. Betul. This is correct. So it now becomes S1 squared. I will check this. Kenapa buku ni guna S1 squared terbalik? So times sama tak? Kejap Kejap, hang on Kejap. So dia sama tak jadi macam ini? Sigma 2 squared over S2 squared bahagi dengan sigma 1 squared over S2 squared is equals to sigma 2 squared over S2 squared times S2 squared over sigma 1 squared. S1. S1 over S2. Okay, never mind. Just leave this one first, okay? But anyway, this F distribution has got n1 minus 1 degrees of freedom and n2 minus 1 degrees of freedom, okay? And it has F distribution has got a skewed distribution, okay? With Fn minus 1 and n2 minus 1 degrees of freedom, okay? So similar to chi-squared distribution, its distribution is skewed, therefore it is not symmetric, okay? Now, in order to construct the confidence interval for the ratio of variances, we're going to use this statistic. So this is correct, sigma 2 squared over sigma 1 squared, or sigma 2 squared over S2 squared over sigma 1 squared over S2 squared. So therefore, if you look here, okay, if I were to draw my F distribution, since I'm going to use sigma 2, the second population over the first population, therefore my F distribution is going to be 2, 1 as well. Okay, second population, then the first population. So this I will use, so this is 1 minus alpha, this is going to be F alpha over 2, and 2 minus 1, and 1 minus 1. Okay, so in order for me to construct the confidence interval for sigma 1 squared over sigma 2 squared, I'm going to use especially the reverse of the population for my F distribution. So here I've got 2, 1 rather than 1, 2. Okay, since this is not my sample estimate, I'm just going to use an F distribution with a reverse order. Okay, but you know that when you want to use, when you want to do the ratio of variances, the best point estimate for sigma 1 squared over sigma 2 squared is still S1 squared over S2 squared. But for the purpose of constructing my confidence interval, I'm going to use a statistic which is the reverse. Why? Because this is the reason why. So when I want to do my limits, therefore, so this limit is going to be okay. So this interval can be translated to this equation, right? So I've got limits here, 1 minus alpha over 2, f alpha over 2. For my f is equals to 1 minus alpha. If I manipulate f, so this f, I'm going to use this statistics, which is sigma 2 squared over S2 squared over sigma 1 squared over S1 squared. So I'm going to use this definition of that reverse formula just now. Okay. So if I rearrange this, in the end, I will get that my estimate of my point estimate of sigma 1 squared over sigma 2 squared. Because this is our aim. Sigma 1 squared over sigma 2 squared. So if you manipulate this, you will get that. So you can see that since this is my best point estimate for sigma 1 squared over sigma 2 squared. So the best point estimate for this one is S1 squared over S2 squared, correct? So for my left and right limits, my upper and lower limit, I will still have this value, sigma 1 squared, S1 squared over S2 squared. Now, what is the f value that we're going to use? So you just look, since we don't have a denominator here, it's only the numerator. So here, the smaller value of my f is going to be my lower limit. And the bigger value of my f is going to be my upper limit. So notice that for my f distribution, I'm still going to use this 2, 1 here, because that is how I how this is what I used to construct my confidence interval. Okay, so apa tu? So basically, to make you easy for you to remember, the confidence interval for sigma 1 squared over sigma 2 squared, you start with the best point estimate. You write this point estimate first for your upper limit, a lower limit, and your upper limit. And then you write down the point on the distribution. So in this case, it's this point here, 1 minus alpha over 2 and 2 minus 1 and 1 minus 1. And then alpha over 2 and minus 1 as your upper limit. Okay? But note that, okay, so this would be the formula that you're going to use. Okay? Let's look at at an example. So a quality engineer is studying the diameter of stainless steel rod manufactured on 2 different machines. We've got 2 population here. 2 random samples of 16 and 13 rods respectively are selected, which give the variances of the diameter values of 0.3 centimeters and 0.4 centimeters squared respectively. Assume that the data were drawn from a normal distribution. Construct a 95% ratio of variances of the diameters. Okay. So if you look at the information that's given to you, so if you've got this population here, so uh, this is the information for one population of machine 1, one population of machine 2, each with its information for its sample. So we got that one, 16, 0.3, and 2, 13, and zero point 0.4. Okay. So construct the ratio of diameter. So in this case, it doesn't specify which ratio of the diameter. So here you're going to use, let's say you're going to use 1 sigma 1 squared over sigma 2 squared. So you just take the best point estimate for this, which is S1 squared, S2 squared, as your um, upper and lower limit. So these are the same value, 0.3 over 0.4, 0.3 over 0.4. And then you take the values from your F distribution. So remember that your F distribution is the reverse of the population that you're using here. So for the estimate that you want here. So here, sigma 1, sigma 2, but you're going to use 2, 1 instead. So in this case, you're going to use an F 0.95 of 15 and 12. Okay, sorry, bukan 15, 12. It's patutnya 15, 12 kan? Tapi the reverse is 12, 15. Oh, I'm silap guys ni. Oh, 12, 15. Okay, so it's 12, 15 here. 12, 15. Can you find the value from your statistics table? Can you find F 0.025, 12, 15? Can you find 0.025, 12, 15? Can you find that value in your statistics table? Class? You should get 2.96. Class, can you get that value from the statistics table? Okay, great. Can you find the value of 0.975, 12, 15? Can you find the value of 0.9751215? So can you find it directly? The value of 0.951215? I don't think you can. No, can no. But remember what we have learned in chapter 2. We learned that so in your table it only gives the value up to 0.1. So if you want to find 0.9751215, this is 1 over f 0.0251512. So we have to reverse this and you get 1 over 3.18, which is 0.315. Okay, so in the end you have in the end you will have 0.236 and 2.22 as your limits. Okay. Note, if your question asks for ratio of standard deviation of the diameters, basically you use just the square root of 0.236 and 2.22 to get 0.486 and 14.49. Okay. Are you okay with this? Not interval, huh? Okay. All right. Boleh? All right. So that's it. That's it for parameter estimation. Do the exercises in your book, and I'd like to, has everybody got on board on the quiz? I'm gonna give it today lah. I mean, like, this is just a quick one. I've set it each, there's only 6 questions. I've set one question for three for fifth apa 30 seconds. Only the last question and a few other questions I put for 1 minute. Good. Okay. So if everybody is on board, I'm going to give it to you, and you can. Tapi please do not look at any books. Just use your knowledge in order to apa tu? To jalankan to apa tu nama? To do the quiz. Okay. So tomorrow we're going to do test of hypothesis, which is another chapter. Okay. Right. If you don't have any question, tak ada question kan? Um, okay, je. Apa ni?